Welcome. This laboratory module will explore the use of a thermogravimetric analyzer, or TGA, to determine the Curie temperature for various iron-nickel alloys. In physics and material science, the Curie temperature is the temperature above which certain materials lose their permanent magnetic properties, which can, in most cases, be replaced by an induced magnetism. The Curie temperature is named after Pierre Curie, who showed that magnetism was lost at a critical temperature. The force of magnetism is determined by the magnetic moment, a dipole moment within an atom, which originates from the angular momentum and spin of electrons. Materials with different structures have different intrinsic magnetic moments that depend on temperature. The Curie temperature is the critical point at which a material's intrinsic magnetic moments change direction. There are various forms of magnetism in materials, and these will be discussed next. The class of materials referred to as diamagnetic materials are repelled by a magnetic field. An applied magnetic field creates an induced magnetic field in these materials in the opposite direction, causing a repulsive force. Diamagnetism is a property of all materials and always makes a weak contribution to the material's response to a magnetic field. In contrast, paramagnetic and ferromagnetic materials are attracted by a magnetic field. Diamagnetism is a quantum mechanical effect that occurs in all materials. However, when it is the only contribution to the magnetism, the material is called diamagnetic. Ferromagnetism and paramagnetism are so much stronger effects that when multiple different forms of magnetism are present in a material, the diamagnetic contribution is usually negligible. A material is paramagnetic only above its Curie temperature. Paramagnetic materials are non-magnetic when a magnetic field is absent, and magnetic when a magnetic field is applied. When a magnetic field is absent, the material has disordered magnetic moments. In other words, the magnetic moments are asymmetric and not aligned. When a magnetic field is present, the magnetic moments are temporarily realigned parallel to the applied field. In other words, the magnetic moments are symmetrical and aligned. The magnetic moments, being aligned in the same direction, is what causes the induced magnetic field. Above the Curie temperature, the atoms are excited and the spin orientations become randomized, but they can be realigned by an applied field. The material becomes paramagnetic. Below the Curie temperature, the intrinsic structure has undergone a phase transition. The atoms are ordered and the material is ferromagnetic. The paramagnetic material's induced magnetic fields are very weak compared with ferromagnetic materials' magnetic fields. Materials are only ferromagnetic below their corresponding Curie temperatures. Ferromagnetic materials are magnetic in the absence of an applied magnetic field. When a magnetic field is absent, the material has spontaneous magnetism, which is a result of the ordered magnetic moments. In other words, for ferromagnetism, the atoms are symmetrical and aligned in the same direction, creating a permanent magnetic field. The alignment of the magnetic moments can occur over very wide regions of the crystal, resulting in the establishment of magnetic domains within a grain of the material. In the presence of a magnetic field, the domains can align with the field by way of a process called poling. the more favorably oriented domains grow at the expense of the less favorably oriented domains. The more oriented domains align, the stronger is the magnetic character. To recap, below the Curie temperature, the atoms are aligned in parallel, causing spontaneous magnetism. The material is ferromagnetic. Above the Curie temperature, the material is paramagnetic, as the atoms lose their ordered magnetic moments when the material undergoes a magnetic phase transition. In this lab module, we will be assessing the Curie temperature for a variety of iron-nickel alloys in the region shown on this diagram containing high nickel concentrations. The samples will range from pure nickel down to samples containing as much as 55% weight iron. In this diagram, phase diagram of the iron-nickel system, the magnetic transformation or Curie temperature curve is shown as the dotted curve indicated by the red arrow. So what is a ThermoGravimetric Analyzer, or TGA? It's really a precise balance placed inside of a furnace. For the measurement of a material's Curie temperature, we use a magnet to impose a magnetic attraction to a room temperature ferromagnetic sample, which acts to pull on the sample due to the attractive moment present in the ferromagnetic sample. In other words, it makes the sample appear heavier on the balance. Now I will explain the components of the TGA. The TGA consists first of a sample pan and a hanger wire, both of which are very fragile. So we use a support platform for sample exchanges and magnetic positioning. The sample pan and hanger wire connect to the balance. When the sample is placed in the sample pan, its weight is measured by the balance at the top of the unit. In addition, there's a quartz tube that houses a furnace. Inside the quartz tube is the furnace itself, which is a cylinder that surrounds the sample. Inside of the furnace is a thermocouple, which is positioned to be located just below where the sample pan will sit inside the furnace. The quartz tube that surrounds the furnace is used to create a closed gas furnace environment. The furnace can then be filled with either an inert protective gas like argon or a reactive gas like air. Gas flow of argon into the furnace tube is critical to keeping samples from oxidizing. If the sample were to oxidize, the sample weight would increase. It would also reduce the metallic component of the samples by creating the oxide, which then would reduce the mass that undergoes the Curie temperature effect. To ensure that argon is flowing, we open all the valves between the argon tank and the TGA itself. We confirm the gas flow by inspecting a gas flow meter that's set up in series with the gas line to the TGA. In the video, note the raised bead in the left flow meter. This indicates argon gas flow to the TGA. A plot of the sample weight versus the sample temperature after the magnet is applied yields a transition used to define the Curie temperature. To operate the TGA, we start by opening the Pyrus software, which is used to control and monitor the TGA. Note the TGA icon at the top of the screen. The software has a control program interface that allows the user to program in a specified heating and cooling profile. This may include the start and end temperature of the profile, the heating and cooling rates of the profile, and any dwell or isothermal holds during the heating profile. The sample information is input into this interface, a file name defined for the saved data, along with a file storage path where the saved data will be located. Next, the heating cooling profile is created. In this case, for the experiments of this module, a single profile will be used for every sample, so that each sample is analyzed identically. The profile uses 4 steps. The initial step is used to heat the sample to 300 degrees C and hold there for 1 minute. 300 degrees C is well below the Curie temperature for the iron-nickel alloys in this experiment, and this step allows the furnace and sample to come to thermal equilibrium. Step 2 involves heating from 300 degrees C to 700 degrees C at a heating rate of 100 degrees C per minute. This allows the sample to be heated above its Curie temperature. At the end of this step, step 3 will hold the furnace and sample at 700 degrees C for half a minute to stabilize the system once again. Step 4 involves cooling back through the Curie temperature and below to record the magnetic phase change hysteresis loop. To set up the sample in the pan, we use the platform to support the pan in the basket. Be careful to keep the basket on the wire hook. Remove the test sample from the bag using tweezers to place the sample into the hanging basket sample pan. Gently lower the platform to allow the sample pan to hang, and then swing the platform out of the way of the furnace. At this point, make a note of the sample weight. Positioning and raising the furnace. The right-hand side of the control panel window in the Pyrus software has control buttons, which when you hover the mouse pointer on top of the icon, a small descriptor box will appear explaining the function. Go to the Raise Furnace function. Press that button, and the furnace will rotate into alignment with the balance, and then rise to seal against the O-ring located above the hanging basket surrounding the top quartz tube. At this point, the furnace will be surrounding the sample hanging basket. The thermocouple is positioned inside the furnace just below the sample basket. Ensure that the thermocouple is not contacting the hanging basket or the sample pan. This can be detected by the sample weight changing from the value before the furnace was raised to after the furnace was raised. Allow the vibrations from the furnace positioning and sealing against the O-ring to settle. When the sample pan has settled down, as denoted by the weight of the sample becoming nearly constant and very close to the weight noted before raising the furnace, then we can zero the sample weight. The sample does not need a recorded weight at this time, as we are only interested in the apparent sample weight induced by the magnet that will be surrounding the sample, and the subsequent loss of that apparent weight when the sample goes above the Curie temperature. The zeroed sample weight is displayed in the top icon bar. Positioning the magnet. Position the magnet on the support platform and position the platform so that the two arms of the magnet surround the sample pan position just below the pan height, so that the magnetic field pulls downward on the sample, but the pan remains centered in the furnace, not touching the side walls of the furnace. Note the increase in the sample weight and adjust the position of the magnet to maximize the apparent weight of the sample while ensuring the sample pan is hanging freely. The magnet vertical position is adjusted to maximize the weight, while the magnet horizontal position affects the hanging basket position within the furnace cross-section. Once everything is aligned and the weight is maximized, then the apparent sample weight must be recorded. Along the right side icons is a button to record the sample weight. It is important here not to re-zero the sample weight, but to record the current weight. Select Sample Weight button and the sample weight will be recorded. Double check everything now to make sure it's ready to go before initiating the heating profile. Now to start the test. To start the test, select the top right icon that contains a small drawing of the TGA with a graph overlaid on it. This is the Start-Stop button. This button is used to start the profile that you have designed, and as well as being able to stop it if necessary. Monitoring your data during the test. During the test data of the sample weight and sample temperature will appear in the associated data boxes along the top of the control display, as well as plotted in the graph. Scaling of the y-axis data may be necessary to visualize the small changes in the sample weight. The x-axis will auto-scale as the temperature increases. Here, note the small drop in the weight between 360 degrees C and 375 degrees C. If we increase the y-axis scale in this region, we can see this weight change in a more pronounced manner. After the furnace temperature reaches 700 degrees C, it will begin its cooling cycle. During the cooling cycle, cooling is achieved primarily through convection between the sample and the furnace with the flowing argon gas. Data analysis. Note once again the small weight change of the sample. The original sample weight was just under 2 milligrams. The weight of the sample above the Curie temperature was close to 0 milligrams. So we can rescale the y-axis to just bound this scale from approximately 0 to 2 milligrams. Both the y-axis and the x-axis can be rescaled to allow more detailed inspection and assessment of the phase transition and the associated Curie temperature. Your plot should be sample weight on the y-axis and sample temperature, not time, on the x-axis. We are trying to assess the Curie temperature, so the sample temperature needs to be one of the two axes. In this case, it is the x-axis. Assessing the Curie temperature. To best assess the exact Curie temperature, one can take the derivative of the weight versus temperature data, which will have a significant inflection at the Curie temperature, noted by the bottom of the derivative curve. We then use the feature in the software for deriving the onset temperature from this data. The onset temperature is determined by finding the intercept point between two lines drawn tangent to the data on either side of the highest temperature portion of the magnetic phase transition. By convention, the Curie temperature is taken as the lowest temperature at which all the magnetic character is lost. In this example, the Curie temperature is determined to be 373 degrees centigrade. Finally, this experiment is to be repeated for each of the remaining iron-nickel samples in an identical manner to what we did here. Then, the resulting Curie temperature data, as a function of composition, should be plotted against the existing phase diagram data for the Curie temperature curve on the iron-nickel phase diagram. For each test, use the plotted data to determine the Curie temperature of each sample. Since you may or may not have access to the Pyrus software, you can determine the onset or Curie temperature in the same manner by drawing tangents to the curves on either side of the inflection and find the intercept of those two lines. Good luck.